I welcome you all for this presentation. In this presentation, we are going to discuss about one of the substitution techniques, that is Hill cipher. This is the overview of this presentation, introduction to Hill cipher, then example of this Hill cipher, then another one substitution technique. Actually, this presentation is mainly for Hill cipher, but with this presentation, we are concluding the substitution techniques. So one famous substitution technique is there, that is the one-time card. Then I have given some practice problems related to Hill cipher, followed by summary of this presentation. So Hill cipher. This Hill cipher was invented by L.S. Hill in the year 1929. See how old was this Hill cipher, but now also we are learning this Hill cipher. And how the name was given means this the name of this cipher is given from the name of the inventor of this cipher. So I already told you that if you are also coming with some ciphers means you can give your name, your friend's name, because Playfair, the inventor of Playfair cipher gave his friend's name, that is only Playfair. Likewise, Hill cipher, he himself given his name, Hill cipher, Hill. So this way we can also name some of our ciphers. So here the input to the Hill cipher is string of English letters, that is A, B up to Z. So we know the equivalent number for each and every alphabet, that is 0 to 25. Then we are having an n cross n matrix K with entries drawn from 0 to 25. The matrix K serves as a secret key. For any cipher, there is a key. So here in this Hill cipher, the key is of a matrix. So but it is a square matrix. 2 cross 2, 3 cross 3, likewise. So based on the matrix only, we have to select the blocks in a cipher. So here we have to divide the input strings into blocks of size n. Then we have to identify A equal to 0, that is we have to write the equivalent numerical of each and every character. And then we have to perform encryption. How we are performing encryption means just we are multiplying each block by K. Then we have to reduce mod 26. This way only we are performing the encryption in Hill cipher. It is very simple. Just we are multiplying the given block. How we are splitting the block based on the size of the matrix. Then each block is multiplied with the key. Then we are reducing to mod 26. Then decryption, it is a reverse process, but here the key we have to take the inverse of that K matrix. So matrix inverse you have to aware of that in performing the decryption process in the Hill cipher. So the decryption must be the inverse function of the encryption function. That is, it is required that K inverse K equal to IN mod 26. You know what is IN? It is an identity matrix. That is, if we multiply K with the inverse matrix, then we are getting an identity matrix, that is IN mod 26. Provided that dit K has a multiplicative inverse. When we call the inverse of a matrix exists, determinant K has a multiplicative inverse mod 26, then only it is possible. That is, if dit K and N has no common factor, the inverse of K can be computed by the adjoint formula for matrix inverse. You please go through the inverse operation in matrix. For 2 cross 2 and 3 cross 3 it's enough. Beyond that we are not going to look into. Nowadays many inverse calculators are also available online, so you can use it also, but you have to know how to compute the inverse of a matrix. So the inverse of an integer mod 26 can be obtained by trial and error. That is one way, but here we are not doing like that because we know the extended Euclidean algorithm to find the inverse of a number. So using extended Euclidean algorithm, you can find the inverse of an integer here. No need to go for trial and error. And I have given you an example here for this Hill cipher, how the encryption and decryption process is performed. Here coming to the encryption, the plain text given is love, L-O-V-E, only 4 characters are there. And the secret key is a 2 cross 2 matrix. So if it is a 2 cross 2 matrix, how many blocks we have to take? How many letters in a block? 2 letters in a block. So you have to split the given plain text into 2 blocks, L-O and V. Then LO, you have to find out the corresponding numerical digit. That is, for L it is 11. Here for your convenience it is given, for L it is 11 and O it is 14. So LO, then you have to multiply this with the matrix. First you have to have the matrix, then you have to have this value of L and O. How to perform matrix multiplication? You please recall that. Here this way we have to perform, that is 20 into 11, the 20 into 11 plus 3 into 14, then 15 into 11 plus 7 into 14. So this way only we have to perform, then we are getting 262 and 263. But don't take as such, we have to perform the mod 26. So we are getting 2 and 3. Likewise you have to perform for VE. The equivalent numerical of V is see here 21, and for E it is 4. So 21 and 4. The same way you have to perform matrix multiplication. You are getting 432 and 343. Then you apply mod 26, with that you are getting 16 and 5. So this is the value. Then you have to take the, how we are converting. Now we are having the numerical. How we are converting into ciphertext, because plain text is the text message. So ciphertext is also obviously a text message, but it is some other value, right? Some other letters on that. So here we are having 2, 3, 2, 3, 16 and 5. For 2 it is C, for 3 it is D, for 16 it is Q, and for 5 it is F. So the ciphertext is C, D, Q, F. So this way only we have to perform encryption using Hill cipher. It is very simple. Then how to decode it? Because decryption is only somewhat difficult. Difficult in the sense, if you know inverse, then it is simple only. So given CDQF and the encryption matrix, same matrix only, how do we decrypt it? So we need to compute the inverse of this matrix, inverse of key matrix. So K inverse we have to find out. So we have to remind that all arithmetic are mod 26. Always you have to know that whatever value we are having, we have to convert it to mod 26. That is very, very important. So there is no fraction, and care should be taken in computing the multiplicative inverse mod 26. Here also multiplicative inverse we have to compute. Fractions are not allowed. So these 2 points you have to always keep it in mind while performing the decryption in Hill cipher. So here you see the determinant of 23, 15, 7 is equal to 20 into 7 minus 3 into 15, which is 17 mod 26. Then what we need to do is we have to find out the multiplicative inverse of this one, 17 inverse mod 26. In the previous presentation I have given you this problem to find out the inverse using extended Euclidean algorithm. So you know the result, I think so, and I have already shown you using the calculator also what is the value. So 17 inverse mod 26 is 23. Not 2 power 3, it is 23. So 17 into 23 is equivalent to 1 mod 26. Here just trial and error approach is given, but we don't want to go for this method because we know the algorithm to compute the multiplicative inverse. So you have to use extended Euclidean algorithm to find out the inverse. So 17 inverse mod 26 is 23. We already know. Now we have to compute the inverse of mod 26, that we already know. Then using the formula of 2 cross 2 matrix inverse, we have to find the inverse of the determinant also. So for 2 cross 2 matrix, how we are finding the inverse in the sense AD minus BC, the whole inverse into, here you have to just replace the symbols alone. Here this one you have to exchange it, D and A you have to exchange it. Here you have to insert the minus sign. Then if you do like this, means here we are having 23, 15, 7 inverse equal to 17 inverse into this exchanged value, this determinant value we are having. So what is 17 inverse? It is 23. So 23 into this value minus 3, also mod 26 you have to do it. That is minus 3 plus 26 equal to 23. So we are getting 23. Then minus 15 plus 26 equal to 11. So here 11. 7 mod 26 is 7 only. 20 mod 26 is 20 only. So no issue. Then we have to perform the matrix multiplication. 59 19 18 mod 26 we are getting. So this is the value finally we got using this K inverse. Then you have to use that matrix, that is the K inverse, that matrix with the CD and QF ciphertext. Here also we have to divide into two parts. Then you have to normal matrix multiplication you have to perform, and you have to take the mod 26. So finally we are getting a value like this 11, 14, 21, 4. The equivalent is LOVE. So now we decrypted and we obtained the plain text from the ciphertext using Hill cipher decryption. Another one very important substitution technique is one-time pad, because all these ciphers are vulnerable to some attack. But one-time pad, except one-time pad means if a truly random key, as long as the message is used, the cipher will be secure, is called as one-time pad. So the key, whenever you are generating a key, always the key must be random. Only one time only we are using that particular key, means then only this cipher is secure. Otherwise it is not secure. So it is breakable. So is unbreakable since ciphertext bears no statistical relationship to the plain text. Since for any plain text and any ciphertext there exists a key mapping to one another. So we can use the key once, though the problems in generation and safe distribution of key is there, but it is not vulnerable to any attack. So as far as possible, if you are designing a very good crypto system, the key you have to generate using this one-time pad concept. So I have given you some problems to practice, but here the key size is 3 cross 3. So you have to know how to find out the inverse of 3 cross 3 matrix. It is somewhat different. You please go through the materials, the earlier mathematics materials, or in the net also it is available how to find out the inverse of 3 cross 3 matrix. You please go through it and try to solve this problem. So in this presentation we discussed about introduction to Hill cipher, example of Hill cipher, both encryption as well as decryption, then one-time pad, and I have given you some problems to practice. Thank you.